So in this video, let's look at solving for the magnitude and the direction of the magnetic force. So the name for the magnetic force is called the Lorentz force. And so this is the force that acts on a charged particle when it moves through a magnetic field. Either a particle by itself, so imagine like a proton shot through a field, or you could have a current flowing in a wire because a current is a bunch of charges moving, right? So the equation for it, for the Lorentz force, is the force is equal to the charge Q times the cross product of V and B, right? That X stands for cross. It's a mathematical operation. So it's V cross B. Let's say I take a positively charged particle, right? And it's got a velocity going this way, and it's going through a magnetic field pointing this way. So what the cross product is, to get the magnitude of it, right? It's how perpendicular these things are, right? And so you can tell in this case, they're at a right angle to each other, right? And so the way you can kind of like eyeball when you have two vectors is to look at the area that they make. So imagine they make a parallelogram, right? This area represents the magnitude of the cross product of V and B. So at 90 degrees, when these two vectors are perpendicular to each other, you get the maximum area in between those vectors, and that means you get the maximum force from this. And so you would represent that on here by drawing this vector coming this way. That's the way the force vector would point. It points at a right angle to those two, and the direction depends on something called the right-hand rule. We'll use that in a little bit. So what if it's not 90 degrees? Okay, so what if it looks like this? So in this case, this vector has an angle here that's not 90 degrees, right? So the magnitude of this vector, of the resultant of these two, is still represented by the area, right? So imagine, again, making a parallelogram, right? So if you've added vectors before, like the parallelogram method, if you bring this one over here, the area of these two vectors would kind of go out to there. And so you can kind of tell that as this is getting smaller, you see how these two vectors, when they start perpendicular, as those two get more and more parallel, this area that's defined by that parallelogram that it makes is going to get smaller and smaller and smaller until you reach, you know, the obvious conclusion where they're parallel and you have no area, right? So as the area decreases, the angle approaches zero and the force is going to approach zero also. So the way the force here would look, it's going to get smaller, right? So when I draw that vector, it's going to have gotten a little bit smaller in magnitude. So see how over here it's big? Here it's getting smaller, and as these two vectors would get closer together, get smaller and smaller and smaller and smaller until this point right here where there's no cross product, the force is zero, right? Because those two are going to be parallel to each other. Here's two vectors, right? My velocity and my field vectors. If I wanted the dot product, I want to know how much this one falls onto it, right? So if I think of this magnetic field vector, it really consists of some that way and some that way, right? And so this one down here is the one that falls onto the velocity vector, and that was our dot product, right? That's what we did with flux and with work and stuff like that. So there's my angle, right? So I used cosine to get that. But in this case, I want to know how perpendicular they are. So I would care about how much this component is perpendicular to my velocity vector. So if I use cosine to get the dot product of the shadow of it, I'm going to use sine for this one. So when I do my equation, right, instead of writing it like this, it's easier to write it like this. The charge Q times the velocity times the magnitude of the magnetic field times the sine of the angle between the two vectors, right? And so you can see here, 90 degrees, sine of 90 is 1, so that's where it's going to be a maximum. You don't even need the sine theta, right, because it's 1. And then as that angle starts approaching 0, the sine of 0 is 0, right? So this whole thing would go away to 0, right? And then anywhere in between, it's going to be some amount that's not quite the maximum. Okay, so let's say I have a wire that looks like this, right? And I've got a current running through it. And so I've got a magnetic field, right? I'm going to say my magnetic field looks like this. It's pointing upwards, right? So there's my field. So the wire has a current flowing this way, right? Current is charges, right? So those those charges are going to be interacting with that field, this little area right here. I'll call that the length L. If force is Q times V times B, right? I can think of that in terms of current and length, right? So Q is charge, and I'm multiplying it by velocity, which is in distance over time, right? Basically, velocity is how far you go in a time. So that's delta x over delta t. Okay, that's the same thing as if I did current, right? So current, we know, is the flow rate of charge. It's dq dt. So if I multiply current, which is charge divided by time, by a distance, which is length, you measure length and distance. Notice these say the same thing. They both come out to delta q times x over t, right? So I can also write this equation, instead of charge times velocity, I can write it as current times length. And it would look like this. So for the Lorentz force, right, the equations you'll see on your formula sheet, its force is charge times velocity times the field times the sine of the angle between the two vectors, or current times the length of the wire in the field, not the whole wire, right, because nothing's happening out here. It's got to be in the field times the sine of the angle. So this will get you the magnitude, but we've got to use the right-hand rule to get the direction.